to introduce our friend Sven-Ake Wegner. Sven was educated in Paderborn in Germany, and he did the Diplomarbeit under the supervision of our late friend Klaus Bierstedt. And he did the thesis under the advice of Klaus and I, and the thesis was presented in Valencia here in this university in 2010. And after that he got several postdoc positions, research positions all over the world, let's say. He's the Marco Polo of Paderborn. He had research positions in Wuppertal in Germany, Novosibirsk in Russia, Poznan in Poland, Astana in Kazakhstan, and Paris in France. So this is not so bad. But if you believe that this is something that he is brave, you will. He was even braver because he got a senior lecturer in the United Kingdom, which is even more dangerous nowadays than the other places. In 2020, he relocated in Germany, and he is research fellow now in the University of Hamburg. And since this year, he is the main researcher of a DFG project, which is called Higher Homological Methods in Caribbean Categories. Today, he will speak about the derived category of the LB spaces. Pleasure to have you here. Please.
Yeah, thank you very much, Pepe, for that nice introduction, and thank you for having me here. It's really a pleasure to be again at Spain after, I think, 5 years.
Sorry.
And I think 13 years since I presented my thesis here in this very room. So,
yes.
It's really a pleasure. Okay, so I start with the first chapter on abelian categories. And so first thing is definition. So before I tell you what's an abelian category, I tell you what's an additive category. So an additive category consists of firstly objects. Maybe this shot's not so good, I don't know. So objects, which I call capital letters usually, X, Y, Z. Then of morphisms, which I denote by small letters, so morphism from X to Y. And these morphisms, so if you fix X and Y, then all the morphisms from X to Y form an abelian grouping. Okay, and third condition, we have a composition, and the composition should work well with this abelian group structure, so we require that the composition is bilinear. Okay, and then we call such a category abelian. If, again, three things hold. So first is every morphism F has a so-called kernel, and that means if I write here my F from X to Y, then the kernel, I call this kappa, is a morphism with here some object, maybe I call this just K, yeah, such that it makes this composition 0, and it's the best morphism that does that. So if I take another morphism here that also makes this 0, then that factors uniquely through that kernel. Okay, and that means if you now think of, I will come to that in a second, locally convex spaces or Banach spaces, it means you have to ask what is this K and what is this kappa. Yeah, and that can depend on the category, yeah, what that is. or if it even exists. Okay, then the second condition, maybe I write that here. Every morphism also has a co-kernel. So every f has a co-kernel, and that's just defined dually in the sense you turn all arrows around. Yeah. So I write here dual definition. Okay, and the third condition is, for that we have to work a little. So in the following diagram, so if we take a morphism f from x to y, we can now, thanks to this first condition, write down here the kernel, and I abbreviate it with this. Yeah, and here we have this kappa, and we can take here the co-kernel of this f. Let's call this gamma, and now we can take off this kernel here again the co-kernel. So co-kernel kappa, and here of this co-kernel we can take again the kernel gamma, and now you have to play with this property here and with the dual property, and then you see that you get here a morphism that's called f bar, which makes this here commutative. Yeah, I will write this down for vector spaces in a second, then you see that it's something very, very obvious. But you can do it also in this abstract way. And then we require here in this diagram this f bar to be an isomorphism. So in this diagram, f bar is an isomorphism. Okay, so that's the axioms. And 3 example. Let's look at vector spaces. Of course, not so interesting, but a good example to start with. So if you have a linear map between vector spaces, then of course your kernel is what you expect. Yeah, and the co-kernel is also what you expect. And if you take that of this the co-kernel here, of this inclusion of the pre-image of 0, you get then this quotient here. This is f to the minus 1 of 0. And here you get just what you kill here in this quotient. So you get this. And this map f bar is the obvious map here. And you know that this is an isomorphism. Okay, so that's not so interesting example. So let's go to non-examples. So 4 non-examples, and I start with Banach spaces, and well, let's write down what's the kernel. That's still the pre-image of 0, and you endow it with induced topology or subspace topology. And then you check this condition. And so that looks not so bad. But now you see already the problem. If you want to do this here, then let me take different color. Yeah, then here you need to take the closure. And that means you get here also a closure, and you see already where this thing goes wrong. Yeah. So I write here, this is y mod f of x bar with quotient topology, and you see that this f bar will always be linear and continuous anyway, but it will be always injective here. It will have a dense range, but it will not be surjective. Dense range in general not surjective. Yeah, very concrete. Take this here for f. Yeah. All right. So, and the same kind of thing you can do for Frichet, yeah. Frichet spaces, for Hausdorff topological vector spaces, Hausdorff local convex spaces, LS spaces, many things we all like. Okay. The second class of examples, LB spaces or non-examples. LB spaces. So let's go first here. Here things go well, yeah, because that thing is again an LB space. But here things can go wrong. So as a vector space, this needs again to be this one here. But if you take the subspace topology of an LB space, that might not be an LB space. So what you have to do here is you have to, if your initial space is a limit of some sequence xn of Banach spaces, then you have to take here these intersections with each step and take then the inductive limit of these. And this gives you maybe here a finer topology. So I call this, use here this B for that. And then you get that the induced map here is still injective, but in general you lose also this dense range. Yeah, so it might happen that this F bar has not a dense range. Yeah, and that's, I mean, you need a tricky example to see that this really can happen. That is, based on an example by Grothendieck, and I think that was then in a paper by Pepe and by Susanne, and it was not formulated in this way here, but they used this example to do something similar, and Dennis, Zeke, and me, we then saw that it answers this question here. So it has a little tricky history, that problem as well. Okay, and the same thing.
Maybe you should tell the audience what you understand by an LB space.
Okay, so an LB space.
Maybe everybody knows.
Sorry. So an LB space is an inductive limit of countable inductive limit of Banach spaces, which is Hausdorff. So I assume this topology, the inductive limit topology, exists and is Hausdorff. Okay, and you can do the same thing here for Hausdorff bornological spaces or ultra-bornological spaces. That so there are more examples in this class here. And third group of examples. So let's start with complete locally convex spaces, and then. Here things go again well. So here you just get pre-image of 0 with subspace topology. But here things go wrong, because it can happen if you take a quotient that this is not complete. Yeah? So here you have to take this thing with a quotient topology, and then you have to take the completion of that. Yeah, and that means your morphism down here is has always a dense range. So this you see immediately. So dense range, but in general that can happen that it's not injective. What you get, yeah, in general not injective. So you can take this classical example due to Köthe, where the quotient is not complete. And then Dennis Zeke figured out how to use this in this setting to construct something where you see this space to be injective. Okay, and by now I wanted to write here, this same thing happens for PLS spaces, PLN spaces, PLS W spaces, and maybe more. So that's also something that occurs in a lot of categories that show up naturally. All right, now you might get here the impression like usually one side is good and the other side is bad, right? So either for kernels things work out nicely and co-kernels get messed up, or the other way around. But it can also happen that it both gets you get with both in trouble. So for instance, if you take LSW spaces, just want to write it down. And there's also no guarantee that that any of this works. So that's the last example. If you take, for instance, complete bonological spaces, then at least I don't know if kernels even exist, yeah, because if you take the associated bonological topology, that
What did you write?
complete bonological spaces.
Okay.
Because if you take you have to do it like, I mean, you can say I do it like here, take the associated bonological topology, but then you can lose completeness because you make it finer. Then you can, well, you cannot really say here, I want to take the completion because there's a result that says as a vector space it needs to be this, needs to look like this. So I guess it's wrong. And here you run into more or less the same problem. This is bonological, but if you complete it, you can lose it. Yeah. So it's not clear to me if kernels and co-kernels even exist here. Okay. So that's, now you see the class of examples that I like. And now I have to tell you about the derived category.
LSW are these LBs which the linking maps are weakly compatible.
Yes, exactly. So, no, 2. Derived categories, and let's say here A is abelian. So none of these strange things for the moment. So definition, we start with the following category. C of A, yeah, that's the category of chain complexes over A. So category of chain complexes, that means the objects are complexes. That means you have here such a co-complexes, to be very precise. I leave it like this. So you have here a chain of morphisms like this, and here you have so-called differentials, and they are like this. That if you compose them, then you get 0. So if you compose two consecutive ones, you get 0. Okay, and morphisms. So if you have two such complexes, then a morphism, that's a y here, is a dot. If you have two morphisms, so let me write that here down. And here with y's, then you can guess what a morphism should be. It's here a system of morphisms in your initial category A, so that's not the pre-image here, of course. Which make all these squares here nicely commutative. So here you have now differentials dx, and here differentials dy. Yeah, so these squares should be commutative. And then you can define for such a complex the cohomology. And let's start. I only write it down in degree 0, but you can take here also the other degrees. It's just for convenience here because this I wrote down. So you take here the kernel of dx0, and then by you can see that by that condition here, the range or the image. I mean, in a abelian category, we don't have to be careful there. The image is contained in the kernel of the map before, so you can here mod out the image of dx minus 1. Yeah, and then you can do the same thing on the other side. So down here for y. maybe I don't write that here. So that is then h0 of y naught, and then you have to go here through that diagram, and you see your map f induces here a map from here to here, and that's then h0 of f dot. Okay, and now comes the definition of the derived category. So that's d of a, derived category of A, and that's a bit disappointing. The objects are just the same as here, so complexes, same as C of A, but the morphisms we change, and I first give you a wish list. Yeah, so how do we want the morphisms? We want the morphisms such that all these maps f dot here that lead here to an isomorphism are isomorphisms already in our new category.
Can you repeat that?
So I write it down, then I
No. Okay.
and then I say it again. So such that f dot is an isomorphism if and only if Hn of f dot are isomorphisms for all n. Yeah? So if two complexes have the same cohomology, then I want that they are already isomorphic in my category.
Im is the same that you call co-kernel.
Sorry?
The image is the same that you call co-kernel before.
Where the image is the kernel of the co-kernel,
Okay.
if you want to make that form. But yeah. In an abelian category, you don't have to be so careful. There, you can also think of this to be the co-kernel of the kernel because it's the same. Yeah. Okay, so that's what we want, and maybe first I tell you why we want that. So I hope I'm making this Spanish question mark right. So why do we want that? So first thing, so three reasons. First thing, if you like derived functors, and I know some of you did this X1 and Prosh1 and Tor stuff, then how do you in an abstract way define the derived functor? On some object, you take a resolution of this, and then you apply the functor to that resolution, and then you take cohomology. And you have to show them that it does not depend which resolution you pick, what you get out. So it's kind of natural to say, I want a category in which the objects of my initial category are identified with all their resolutions. That's kind of natural to do, and that's what you achieve here. Yeah, so identifies objects of A with their projective or injective resolutions. Yeah. Okay. That's the first thing to say. Second is, if you know, for instance, in functional analysis, you usually don't have projective resolutions. You have only injective resolutions. Some old results. And but there are also categories where you don't have injective resolutions, but you still want to consider derived functors. And then this is the technical thing that was invented in like the 60s to do that. Yeah. So you can here define, using this derived category, in this way you can define derived functors even if you have no projective or injective resolutions, so without resolutions. I write it like this, and The third point is, it is, I mean, you can say, I asked why, you can say why not, yeah? So I can define this kind of animal, and it is some higher invariant, you could say. Like, I mean, if you want to study a category A and it is maybe hard, or you have two categories A and B and you want to know are they the same or not, then you can say it's very hard to decide, but I compute these derived categories and check if they maybe are the same. Yeah. So I write higher invariant. Like you do that in topology with a fundamental group, for instance. Okay, and then, so I hope that was a good reason why. And now, second question is how can you do that? And this looks kind of funny here, right? I mean, I want to make stuff isomorphisms, which is, I mean, isomorphism is a property, right? So how do I make things in isomorphisms which are not? Yeah, but you all know how to do that. Yeah, you just make this formally. Yeah, so wait, I wanted to do here one more thing. So firstly, we call these f dots, which have this property, we call these quasi-isomorphism. And then you make these quasi-isomorphisms formally invertible. Yeah, and when you see the notation, you will see what I mean. So you have here this category with these complexes, and then you do this like a ring localization, and like you define the rationals from Z. You make everything non-zero invertible, yeah, in a formal way. Yeah, and this can be done for categories as well. So that's some technical result, but yeah, if you think of a ring localization. Okay, and now that's now go back to these examples that I had. Then you see, in order to say what these guys here are, I need this cohomology, and for this I need to take here these quotients, and that's kind of a problem maybe because you saw that quotient is somehow tricky in these categories because you maybe don't mod out here what you want. Yeah. You have to do here adjustments. So it would be good to describe this without using this H naught. And that can also be done because, I mean, you can, if you say, hey, here you say which morphisms you make isomorphisms. So which objects become like the same after this localization. And instead of saying this for every pair of objects, you can also say which objects do you kill. So which objects do you make isomorphic to 0? Yeah, because it's like additive, so that should be enough. Yeah, and that is a little bit cheating here because it's also defined by localization, but it's a different way to think about it. So make complexes 0, and which complexes do you need to make 0? Those which have 0 cohomology, and these are usually called exact complexes, yeah, or acyclic complexes. So I write here both exact or acyclic. Zero. So you define this D of A as C of A mod the acyclic complexes. And here's a little technicality. I like to write here K, so that's a homotopic category, and here maybe 2. I mean, you can define this also with C, but this makes the properties a bit better. So this means you can really compute in this category like with fractions. Yeah, so the morphisms are fractions of some morphism in this category. So something like this. And then you have this formally inverted morphism here going in the other direction. So and therefore you need here this homotopic category. But that's a technical trick. Okay. And if you do it like this, then this is often called the Verdier quotient. Okay, so far. So next question then is, what means exact? Yeah, if I'm not in an abelian category. That's the thing we have to answer next. So 3, what means exact? In non-abelian A. And so this is the technical definition. So we take an additive category. So all these examples that I gave you are nice additive categories. So that applies to all of them. And then, I mean, in algebra, this is always basic algebra. This term short exact sequence is always like intrinsic. Yeah, so it's if you have vector spaces, it's an intrinsic thing. But now we make it like extrinsic. So we define what should mean exact or short exact sequence. Yeah, so we say what we mean by that. And so something like this. Or for short, just FG. We firstly call a kernel-co-kernel pair. That's easy. Yeah, so if F is the kernel of G and G is the co-kernel of F. But recall that what this means, so how to compute the kernel depends on your category. So that's not always the same. Yeah? So that's a condition for each category. You have to check what that really means. Okay? And then if a class of such kernel-co-kernel pairs, let's say E, is fixed, so we fix now such a class, and the guys in the class we want to call them the short exact sequences. And this needs, of course, to satisfy some conditions. Yeah? And first, some just notation. So if we have such a class fixed, then we call a morphism F an inflation if it shows up on the left side in such a tuple. Yeah? So if there exists G such that Fg belongs to our class, yeah? And similarly you define deflation, that's the guys that show up on the right hand side. So similar deflation, yeah? So G deflation if there's F such that Fg is in E. And then we say E is an exact structure if now 6 conditions hold, but luckily they come in pairs. So we start with first condition. So we want that all identities are inflations. So for every object we want that the identity is an inflation. Yeah, that is the short exact sequence where here is the identity and here is 0. Yeah, that's what you want, of course. And then let's see if this color works. You take here the dual condition where you write here deflation instead of inflation. So also if here's just the identity, here is 0, that should also be in our class. Then second, E1. if you have two inflations and you compose them, then that should again be an inflation. And the same goes here. We want that also for deflations. Okay? And the last one, push outs of inflations are inflations. So, and I have to tell you what's a push out. So push out means, so you have here your inflation, yeah, and then you take any map here, let's say T, and push out means you can, so this is here included, yes, exist and are inflations. So you can complete this here to a square that's commutative, and it's again the best square. Yeah? So if you have any other square which also makes this commutative, then this factors uniquely through your best square. Yeah? Okay. And again, the dual condition. So then you have here to revert all the arrows, then you get something that's called pullback. And here you write deflation. Okay. So, and don't worry too much about these conditions. I mean, you know, in algebra you do a lot of these category theory, you do a lot of this diagram business, and that's the properties you need to do that, yeah, to prove the technical stuff. All right. So now I can define what are these acyclic complexes, and I can do this without using this H0. So that's what I wanted. So a complex is exact or acyclic if, so let's say the complex looks like this, as we had that, then I say it's exact if it factors like this, and these guys here are in your exact sequence, in your exact structure. All. And this way you can define this without using this cohomology factor. And if you do that, plus some technical conditions that I want to ignore here, then this leads to a definition of this derived category with respect to this exact structure. Okay, so now back to functional analysis. Examples. So, first example, if you take these Banach spaces again, yeah, then that's, as you saw, is a good category still. I mean, it's not abelian, but I mean, if you put up with that you have to close before you take a quotient, then this is, say, still very good. And here you can indeed take all kernel co-kernel pairs, and then you can check these funny axioms here. So you can do homological algebra with all kernel co-kernel pairs in this category here. And what is a kernel co-kernel pair? Because of the closed graph theorem, that just means this is exact as vector spaces. Yeah, because this closedness condition you get for free because the exact as vector spaces means f of x equals g to the minus 1 of z, and that's automatically closed, and then these things become topological embeddings. So this becomes a topological embedding. This is anyway surjective, so hold it. Yeah, so I write here exact as vector spaces, and if you take Hausdorff locally convex spaces, you can do still the same thing, but now you don't have the closed graph theorem, so you have to require here what usually is called topologically exact, yeah, in the literature. So topological exact sequences. All right, and now what is with the LB spaces? So you would maybe hope, well, I have here also a closed graph theorem, so maybe I'm lucky and I can still take all these co-kernel pairs, but you hear already, it's not true. So LB spaces, and surprisingly, there are several interesting classes of short exact sequences. The first is you take these topologically exact ones. That's kind of natural, right? That's like the induced exact sequences that you get from here. Yeah. So I write here induced by this. So all pairs Fg, which are exact as vector spaces, and then what do you have to require then? That it for this topological exactness, because you have this closed graph theorem, it's enough to write that. So this is closed by this, and then this associated bonological topology must be the same as the induced topology of the space Y. Yeah. Or other formulated in a different way, that means f of x is a limit subspace. Yeah? And that is what you expect when you say topologically exact. So I write it like this: f of x limit subspace. Okay, and yeah, let me first wipe here. So yeah, it goes on here. I do like this. So there is indeed a larger exact structure still, and the largest, which is also natural. And how do you get this? I mean, you look back at these axioms, right? And there you have had these two properties here with this push out and pull back, which here meant if this is an inflation, then this should also be an inflation. And if you want that all your pairs satisfy this, then it's a very natural idea to say, well, I just take all pairs where for both sides that's true, right? And that's the maximal exact structure that you get then. And with some work, you can then see that this is exactly those pairs where you have again that they are exact as vector spaces, and I write it here. You have almost, I mean, this was I write first this condition here. Yeah, and this is now must be weaker, of course. The condition is that here only the duals must coincide, and that means this here is a well-locating subspace. Yeah, so f of x well-locating. So also a classical property. Okay, and this is still contained in the class of all kernel co-kernel pairs, and strictly contained. So all kernel co-kernel pairs don't form an exact structure on this category, and I will write that down in the last chapter. So this is paragraph 4. Deflation exact categories, and this is based on joint work with Ruben Henrath, Sondre Quam, and van Roosmalen. And I mean, so if you encounter a problem like this, you want this exact structure, and so I mean, I try to convince you that this is very natural. So you take like the largest class that satisfies the axioms. If all don't, then you take the largest class that does. And the second thing you might want to try, if all don't satisfy all your axioms, you kick out some axioms. Yeah, so you redefine what exact structure means, and hope that this also gives you something interesting. And that's what I want to show you here now. So 9 definition. So again, a additive as before, and we take a class C of kernel co-kernel pairs. And then we say that A together with the C is deflation exact with a conflation structure. So we don't call the C exact structure for obvious reasons. So we call it conflation structure. C if only the op version of the axioms hold. Yeah. So if E0 op, E1 op, and E2 op hold, and yeah, so only this 1/2 of the axioms. Some also call it a one-sided exact structure. And then you have to work, and then you see it's enough to define also this thing here by this Verdier quotient. Yeah. So again, leads to a derived category with respect to this other class of conflations. Good. So, and so I think that was 10, right? I always mess the numbering up. So 11 example. So this AB spaces, if you take their, I call this here now epsilon E all, yeah, so this, but it's not an exact structure, but I stick to this E, yeah. Then this is deflation exact. But not exact. Yeah, and indeed, you have that for any pullback square. So if you have some morphism G here of AB spaces, and you take this this pullback, and then you get here something like this, and here some morphism G prime. It's true if G is a co-kernel, then G prime is also a co-kernel. And now you can ask, so how do you prove that? You first have to check what are the co-kernels. Yeah. So when is a map the co-kernel of some other map? And in these AB spaces, it turns out it's the surjective maps. So if you take, yeah, so the co-kernels are the surjective maps in this category. And On the other hand, for push outs, it looks not so good. So if you have here some f, then there is an example where f is a kernel, but f dash down here is not. Yeah, and the kernels in this category are the injective maps with close range. So it's not arbitrary injective maps, and it's also not needs not to be a limit subspace. Yeah. Okay. And yeah, maybe a few minutes left. Say this just orally. I mean, in this Emax, yeah, I mean, if you see this, then you see that the co-coordinates are like good, right? I mean, the G's have all the nice properties you want, but still here you have to sort out some G's. And not because the G's are like bad and violate your axioms, but some G's might have a bad kernel. Yeah? So although all G's satisfy your nice property here, because you need pairs where both satisfy that, and not all kernels do that, you get here like really, so certain co-coordinates are here missing. They are not shown up in an exact sequence. Whereas here, so here you have them again all. Yeah, all co-coordinates, and then you take their coordinates. Okay, and there should be one theorem, right? So if you now look at these derived categories, then you have here natural functors here. So if you take your AB spaces with the topological exact sequences, you get this derived category. Then you get a functor into the AB spaces again, so derived category of AB spaces with this maximal exact structure, and then you get another functor into this derived category of this. So E all. And none of them is an equivalence. Yeah. So which aren't equivalences. So I have three distinct, pairwise distinct derived categories. And second, now the question is, why do I want this strange thing here? I have already two, which are different, so why do I even need a third? And the reason therefore is, there is a natural equivalence. From the last one to something that I cannot explain now in more details, to a category of formal quotients of AB spaces. So you take monomorphisms, that's like a quotient. You consider this as a quotient that you don't take, yeah. And then you also here make something invertible, and this is firstly abelian. Yeah, so your non-abelian category is derived equivalent to an abelian category in a very natural way. And these things here, these formal quotients, have been studied by this Lucian Walbrook since the 60s. Yeah, so this is also something that has been around, not for AB spaces, but for Banach spaces, for homological spaces, and so on. I write here formal quotients, yeah, a la Walbrook. Okay, and the very last comment. So that should be, again, a mistake here, 12, and that should be 13. So if you take complete locally convex spaces, you get the dual thing. So then you have to define inflation exact. Take just the axioms without the op. Yeah. Inflation exact. And this inflation exact also applies to all these categories: PLS spaces, PLN spaces, PLSW spaces. So this is again something that shows up in categories which occur naturally in applications also. Yeah? And this is a result by my student Marian Lawson. And I think then I'm done. Thank you very much.
Thank you very much. Thanks. Ben, any questions or comments or anything that?
Just curiosity, because I don't know this subject well, so sorry if I say anything stupid. Your many known examples made it clear that the categories in functional analysis are not abelian.
Yeah.
So abelian categories work very well in algebraic geometry, but not in analysis. Nevertheless, the categories in functional analysis can be fit in these derived categories, these other classes of categories. But what are the expected result with this connection? To use category theory and homology as a tool for functional analysis to prove the results in functional analysis, or do you use the functional analysis to construct new examples of categories in category theory that can be usable as counterexamples of both things?
I would say both, indeed. Thank you. You answered your own question. So when I worked with this group of algebras, they were very interested in this AB spaces as an example that these things really more or less naturally occur. Yeah. So it is a second. Your second point, but I mean that you want to, I mentioned that you want to compute like X and Tor also has applications, yeah, in functional analysis. If you have like a partial differential operator and then you want to know if it has an inverse, then that's something that leads naturally to computing like X. And then you want to compute it like in the natural category. So if your differential operator lives between PLS spaces, then you want to compute this X in the PLS spaces in the natural way. And that means you need, as this has a strange notion of exact sequences, you need like to do this kind of stuff. Yeah.
Okay, thank you.
So let me say that since PLS for somebody in the audience might be not known, the relevance of these categories, PLS or PLN, this means projective limit of inductive limits of Banach spaces which are with
compact or nuclear or
linking maps.
Compact.
And the important fact is that the distribution, the space of distributions belongs to these. So then, I mean, what he indicated is that, let's say, a more concrete question would be, here is your linear partial differential operator between the space of distributions. You may want to know when it has a linear right inverse, a continuous linear right inverse.
And then you take the kernel, and then the sequence need to be split.
You can formulate that in these terms. So this may also. This is the other point of view. This is the only point of view that I was at some point interested in. But did I understand that these LB categories or other categories, if you look at it from the point of view, that this other point of view that you mentioned, that this is something concrete and gives examples of these things that these three things. And so from the point of view of category theory, this might be something else. But
I mean also here, I mean it's the case that that like the natural exact sequences are then are not all kernel-cokorner pairs, which is maybe firstly irritating, but it just sorts out like the bad kernel-cokorner pairs. Yeah.
Mm-hmm.
So you end up exactly with what you want, yeah, which are the good exact sequences. Yeah, so it is. So also this is a complicated example already. So I would say.
Any other thing or any other comment? So if not, we thank the speaker again. Very good.